Hello, welcome to part 2 of the ninth lecture of EEE 157. In this part of the lecture, we will be talking about how we modulate in the baseband and how we transmit the bits over a wired channel. Okay, so the basic technique of transporting a set of bits through a wired channel is if we group them one bit per symbol, and that is in the form of line codes. So this is the process of converting digital data into a digital signal. Okay, so there's more flexibility here. There are different types of line codes. So if we use, for example, the most basic example, I've mentioned this in the previous part. If we represent bit 1 as a high voltage, we represent bit 0 as a low voltage or 0 voltage. The opposite can be true, of course. Like if we represent bit 0 as the high voltage and bit 1 as the low voltage, it doesn't matter. Okay? But the convention is we represent bit 1 as a high voltage, we represent bit 0 as a low voltage. Right? And there are other different ways will be to encode the bits over digital signal, over a wired or a bandpass digital modulation technique. Okay, so the first category of your line codes is in its polarity. So there are three types here for your polarity of your line codes. The basic one is what we call the on-off keying, or the unipolar line codes. So it only has one non-zero level. Okay, and basically, if it's high, right here, then your output is bit 1. Sorry, if it's bit 1, the output is a high voltage, right here. If the output is bit 0, if the input is bit 0, the output is a low voltage. Okay. So there are two different types. We'll talk about the definitions of these later. Okay. So basically, for unipolar, if it's high, it's bit 1. If it's low, it's bit 0. For polar line codes, you have two non-zero states and with opposite signs. Same magnitude, opposite signs. Okay. This line code can never be 0. Okay. If you sample a 0 using this line code, a polar line code, that doesn't mean anything. Right? It could either be bit 1 or bit 0, but it doesn't mean anything. Okay? So you have to sample a positive parameter or a negative parameter before you get what type of bit this is. Okay? So normally, bit 1 is the positive and bit 0 is the negative, but it could be inverted. Bit 1 could be negative, bit 0 could be positive. So note that they have the same magnitude, sorry. Okay. And the last one is called the bipolar signaling, or the alternate mark inversion as we call it. It uses two non-zero states, but these two non-zero states are assigned to a single bit, and the 0 state is assigned to the other bit. Okay? So, for example here, the bit 1, the first bit 1 is in the high state, the positive high state. Okay? And the next bit 1, as you can see, is already inverted in the negative high state. Okay? So bottom line here is bit 1 is still in the high state, but bit 0 is always in the 0 volts. Of course, again, you can invert your convention. Could be 0, who is either in the high or the low volt, or the negative, could either be in the positive or the negative voltage, or your bit 0 is in the your bit 1 is in your 0 volts rather. And this table right here is a summary of the advantages and disadvantages of each. For unipolar signaling, the main advantage is it uses less power, right? And it's easier to implement. So you only have one non-zero state. Just pulse it on or off. It's just on or it's just off. So it's easy to implement. And it uses less power. How? If we assume that the high levels are of the same amplitude, let's say this is positive A. For polar, this is also positive A, and the other side is negative A. Okay. So using that, we know that for unipolar, sometimes it's on, sometimes it's off. So sometimes it uses energy, sometimes it does not. Okay. So it uses less power compared to your polar, and your compared to your polar line code. But the problem here is that we have what we call a DC buildup in cable. So if you solve for the average voltage of your polar line code, you get a non-zero voltage. Okay? You have a voltage that is far above zero. So this voltage here uh, consumes bandwidth, okay, that is not used in the transfer of information. Okay? And we don't want any DC buildup in the cable actually. For a polar line code, so the difference between your unipolar and polar line code is there is no DC buildup. But it uses more power compared to unipolar because a polar line code is always turned on. Right? It's also easy to implement. So not easier than unipolar, but it's easier to implement compared to your bipolar at the very least. So this is ranked from uh, hardest to implement, easiest to implement to hardest to implement. Right? So it uses more power, but it's easier to implement than bipolar. And there's no DC buildup for your polar line code here. For a bipolar line code, there's also no DC buildup. Why? Because your positive and your negative are always alternating depending on the occurrence of one. If the occurrence of one is even, then you have no DC buildup in your cable at all if you solve for the average voltage. It's close to zero. If you have an odd number of ones, then you have some form of DC buildup, but it's very small. Okay? So, for a bipolar code, actually, let me correct that. I'll correct this when I upload it. Okay? It actually does not use more power compared to your polar. It uses the same amount of power to your unipolar, in which it is only turned on if it's either bit 1 or bit 0. Okay? So in this convention that you see here, the figure that you see here, it actually is only on if bit 1 is the input. And that is also true for unipolar. It's only on if bit 1 is the input. So it doesn't use more power. It actually uses less power compared to your polar signaling. Okay? And it has no DC buildup, which is the main advantage of it over unipolar. But it's the most difficult to implement. So there's a trade-off here between power use, DC buildup, and difficulty of implementation. And another big advantage of your alternate mark inversion is the inherent timing recovery. So how does that work? Because of the transition between two bits, you can recover your clock if there's a transition between two bits. The problem with unipolar and polar is that if we have a long sequence of bit zeros, okay, your clock could get confused and don't know when to start sampling again. You can only recover the timing if there's a transition between two states. Okay? If let's say for a bipolar signal, if you have a series of ones, then the output will look like this. And there's always a transition between two states for a series of ones. Therefore, we can easily recover the timing just by sending a series of ones. Okay? And that's one big advantage of your bipolar compared to both your polar and your unipolar. Okay. So what if we can't use a bipolar? It's too complicated. How do we recover our timing for unipolar and polar? And that brings us to our second type of line code in terms of pulse duration. And there is what we call a non-return to zero and a return to zero. Okay? The non-return to zero, basically, your pulse stays at that state depending on the bit. It doesn't return to zero, okay, within one symbol period. So as you can see here, if the bit output is 1, then for the whole symbol period, or the bit period here in this case, the output of your line code is always 1, or always high, rather. For the return to zero code, if you have a bit 1 for unipolar, then you will have an output that is going to go back to 0 within the bit period, as you see here. Okay? So, as we know, If we have a pulse that is shorter in duration, it will use more bandwidth. Okay? But if you're using a wired channel, is bandwidth really a concern? Well, it depends on the design of your wired channel, of course. Okay? But it uses more bandwidth compared to your non-return to zero. Okay? So if it uses more bandwidth, then your channel should have a larger bandwidth compared to one when you use your NRZ. But the bottom line here is the advantage of the return to zero code is it has self-synchronization. So for a polar return to zero code, if your input is zero, it will shift to the negative state, but it will also return back to zero within your bit period. Okay? And for one, it will go to the positive high state here, but it will also return to zero at the middle of the bit period. Okay? The best part here is it has self-synchronization. Okay? Even if you have a long string of ones, for example, for a unipolar RZ, you will always get transitions in your line code. If for polar RZ, if you get the absolute value of this symbol here, of this setup here, if you get the absolute value of that, okay, if you get the absolute value of that, you will actually get a pulse train, a rectangular pulse train, and this is already your clock signal, the original clock signal at the source. Okay? Because of this, you can always synchronize your receiver to your transmitter, which is an important thing in a digital communication system, the synchronization between your transmitter and the receiver. Okay? And that's the advantage of the return to zero codes. So if you want an inherent timing without using a bipolar code for your polar and unipolar, then you use a return to zero code. Okay? Next would be some other types of line codes where the codes are not encoded in the signal levels, but rather in the transition between the two signal levels. So one type is the split phase or Manchester signaling, where your bits are encoded in transition. If you have bit 0, then your code will transition from low to high. Right here. From your negative to positive in this case, if it's polar signaling. Okay. If it's bit 1, then your code will be transitioning from from high rather, to your low signal. Okay? Of course, you can reverse that. Bit 0 could transition from high to low. Bit 1 could transition from low to high. Okay? So what's the advantage of this? One advantage is, again, you have self-synchronization. Because your bits are encoded within the transition, you can easily recover the clock every time there's a transition between states. You can easily recover the timing of your transmitted signal. Another advantage of this is that it can use a low power. I forgot to put it here. I apologize for that. It uses a lower power compared to, or rather, it can use a lower power. Okay? Since we're encoding between transitions, you only need to track that transition here using an edge detector or whatnot. You only need to track the transition here. An edge detector is very easy to implement in using an operational amplifier, actually. So you just need to track that transition so you can recover your bits. Okay? Once you track that, you get your bits. Okay? So you can transmit this in a low power and you can still recover your bits without error. As compared to this, when it's very noisy, when it's very noisy, then your bit could transition from the low state and the high state, and your recover won't be able to keep track of what are the bits transmitted. But if you encode in the transition, even if this is very noisy, okay, if you catch the transition, you will be able to decode your bits. Okay, so we can lower the power using split phase and Manchester signaling. Okay, the other one is the mark or space, NRZ, mark or space, where if you have a bit 1 for mark here, if you have a bit 1, your signal will transition from one state to another. Okay, so for example, if we have a bit 0 and we started at the negative value, if you have bit 0, you have the negative value, then when we get a bit 1, we will transition to the other state. Okay? The next bit is 0, so we won't transition to the other state. But once we get another bit 1, we transition to the other state. How can we use this to synchronize the clocks? If we have a series of bit 1s, we have a series of transitions. Again, we can recover the clocks when there's a transition between states. The opposite is true for space. When we have an NRZS, or non-return to 0 space, it's bit 0 that does the transition instead of bit 1. Bottom line here is there's only a transition when a certain bit appears. Okay? There's only a transition between states when a certain bit appears. So this NRZ mark or space here is what we call a digital modulation with memory. So this is a digital modulation with memory. Okay. So since it has some form of tracking the different states, the next output is dependent on the past input, and so on and so forth. And this is a concept reserved for a higher course, especially for you electronics engineering students. Okay, for others, computer engineering and electrical engineering, you don't need to know digital modulation with memory actually. Okay, so anyway, the bottom line here is that a transition only occurs if there's a certain input. Similar to your, I think it's T flip-flop. Okay? It's similar to your T flip-flop. Okay? So, that is your different line codes. Okay? So, the problem with line codes is that you only limit the modulation to 1 bit per symbol. And you can already do a lot of things actually, but what if we want to transmit more bits, but we are limited in bandwidth? Okay? Let's say your channel is limited in bandwidth, but it's not limited in power. You can transmit a larger power here. Then that is where the MRE PAM or MPAM will be used. So this is still a baseband digital modulation, but it uses more bits per symbol to transmit your data. Okay. So PAM here stands for pulse amplitude modulation. Okay. And again, the relationship between the number of bits and the number of symbols is the same here. M is equal to 2 raised to b. Okay. And actually, the polar non-return to 0 line code is actually a PAM code, or a PAM modulation technique that corresponds to 2 symbols, or 1 bit per symbol. So another example of PAM is the quaternary PAM. Okay? So the simplest method here is your 0, 0 is corresponds to the lowest level, and so on and so forth. So your 4 different combinations for the quaternary PAM, your 4 different bit combinations are mapped into 4 different signal levels. Okay? So we have plus 3D, plus D, negative D, and negative 3D. And this is how your MRE PAM works. Okay? Because of this, if we take the different symbols, okay, and map them on a number line, we get what we call a constellation, but more details on PAM. Okay, I forgot about this slide. So the definition of PAM here is you have a symbol sequence. Okay? The nth symbol, A sub n, is taken from this set. Okay? An odd multiple of some parameter d. Okay? The parameter d here is a parameter that defines what we call the minimum distance between each symbol. Okay? We talked about this in the previous part of this lecture. Okay? So we can transmit in PAM, we can transmit any pulse that corresponds to this symbol. So in this example, we transmitted a rectangular pulse, P of t. But generally, we can use any pulse, and by designing this pulse appropriately, you can actually conserve more bandwidth. But again, this is for higher courses. It's not for you. It's not for this course, rather. So the PAM signal S PAM of t can be uh, represented in using this equation. You have your finite duration pulse. For now, it's a rectangular signal. And you have a sub n, which is the nth symbol in the sequence. So it looks like your sample and hold actually. It looks like your sample and hold, but here a sub n corresponds to the symbol depending on the bit for your digital modulator. So here, when b is larger, the power consumed is actually larger, but your system has more reliability. And we talked about this briefly in the previous part of the lecture. We'll talk about this in more detail at the last part of this lecture, the fourth part. Okay? So this is where your constellation comes in. If we take the symbols in PAM and put it in a number line, we have a constellation, a PAM constellation. So the binary PAM has two symbols, one in positive D and one in negative D. If the received signal is here, very high, the receiver will understand that, oh, it's this positive D symbol, it must be bit 1. If for the next one, the quaternary PAM, if the received symbol is here, the receiver will understand, it's positive 3D. Positive 3D, it must be 1, 1. For your 8 PAM, let's say the symbol is here. The symbol is here, it will understand that it's positive 3D, it must be 1, 1. Sorry, 0, 1, 1, rather. So it must be 0, 1, 1, so your receiver can correct that information. So if it's noisy, then if the signal falls in this region, you have an easier correction or the receiver can correct that information. And if you have a larger constellation maintaining D, a larger constellation, you maintain the minimum distance between symbols, you're using more power in your digital modulation. So using more power in digital modulation, we can actually use even 256 symbols. That's a large constellation, but it will use a lot more power compared to your 8 PAM, quaternary PAM, binary PAM, and so on and so forth. Just a note that this binary PAM constellation corresponds to your non-return to 0 polar code. So, to summarize, line coding is used to transmit bits over a wired link, and we can categorize the different line codes in terms of polarity, pulse duration, or if it's a transition between the two states when you encode your bits in a transition rather than the signal levels. The properties of interest when we talk about line codes, if it's able to fit in some bandwidth, if it's building up in terms of its DC component, or if it has a self-synchronization ability. Of course, I also forgot complexity of implementation will always be the property of interest in any communication system. So we're also interested in the complexity of implementation when we talk about line codes. If we're really limited in bandwidth, but we're not limited in power, we can use MRE PAM. So we can decrease the transmission bandwidth for an increase in power. So there's some form of trade-off here. If you want to decrease the bandwidth, you can increase the power so you can fit more symbols in your digital modulation. And this is a unique trade-off in a digital modulation system actually. And we will talk about this more when we're going into bandpass modulation techniques. So this is the end of this part of the lecture. If you have any questions, do not hesitate to leave a comment in the comment section below, or you can send an email to me. Thank you for listening. See you next meeting.